Assalam and welcome everyone. So today we're going to be working on the question on the screen from chapter 5 of the Atkins Physical Chemistry 11th edition textbook. The question is the osmotic pressure of an aqueous solution at 300 Kelvin is 120 kilopascal. Estimate the freezing point of the solution. So the question is telling us that the osmotic pressure of an aqueous solution at 300 Kelvin is 120 kilopascal. So from just this first sentence, we can write out the parameters that we're given. And the first parameter we're given is temperature, which is 300 Kelvin. Next parameter we're given is the value for the osmotic pressure. And this is basically the um, symbol for osmotic pressure. This is 120 kilopascal. So they're telling us to estimate the freezing point of the solution. So estimate the freezing point of the solution. Now, before I go on to solve this question, I want to quickly mention something to you guys. This is a question that tells us the aqueous solution of something. Aqueous, anytime you hear it, is just telling you that the solvent, okay, in an aqueous solution is always going to be water. Because this is very important for us to note because you don't want a situation where you start working and then you start thinking, okay, what is the solvent? So in an aqueous solution, the solvent is always going to be water from, aqua, meaning water. Now, this question has told us two major keywords. They've told us that there is osmotic pressure as well as freezing point. And anytime you hear osmotic pressure and you hear freezing point, you have two major formulas that you're going to be using in a question like this. So they first told us about osmotic pressure and then they told us about freezing point. So I'm going to first of all write the formula for osmotic pressure. So the formula to determine osmotic pressure is simply the Van Hoff equation. And in this equation, we have the osmotic pressure, okay, is equal to the molarity of the solute B, so the concentration of the solute, multiplied by R, which is a gas constant, multiplied by T, which is a temperature. So here, this is the osmotic pressure. Here, this is the concentration or the molarity of the solute, and we denote the solute to take the symbol capital B. So the concentration or molarity of solute B. We have the R, which is simply the gas constant. And of course, we have T, which is simply the temperature. So the reason why I'm explaining this Van Hoff equation is because using the Van Hoff equation, you can see from our work based on the parameters that were given that the osmotic pressure has been given to us in the question, the temperature has been given to us in the question, but we do not know what the molarity or the concentration of the solute is. And R is a gas constant, and of course, a constant is always going to have its own definite value. So in this case, we're going to be using the gas constant. R is equal to 8.3145 kilopascal liter per mole Kelvin. So this is going to be the gas constant. So knowing that we have the osmotic pressure, the temperature, and the gas constant, what is left for us to solve for is the concentration of the solute. So rewriting the formula, we have, first of all, we have this. This is the formula, right, by RT. So rewriting the formula for B, you have the osmotic pressure divided by RT. So that's what this is going to be, the osmotic pressure divided by RT, where we've been given the osmotic pressure. We have the gas constant and we have the temperature. So all we have to simply do is substitute. So you have the osmotic pressure to be 120 kilopascal. So I'm going to substitute that. So 120 kilopascal divided by the value for R, which is just 8.3145 kilopascal liter per mole Kelvin, okay, multiplied by temperature, which is just simply 300 Kelvin. So 300 Kelvin. So of course you cancel out all of the units, like units, you cancel out the Kelvin here, cancel out the Kelvin here, cancel out the kilopascal, cancel out the kilopascal. So what we end up with is B, the molarity of B, or the concentration of B, is just simply going to be 120, which is the numerator, divided by the product of the denominator. So 8.3145 multiplied by 300 is simply going to be 2,494.35 liter per mole. We can do the division for that, and you have 120 divided by 2494.35. You have the molarity to simply be equal to 0.048108726. And of course, the inverse of liter per mole will just simply be mole per liter. So this is actually the concentration of the solutes. We don't know what the solute is in this case because we're not given. So the fact that the question just says solute B, we're just going to call it solute B. I wanted to mention that if you were given, for example, the concentration of the particular solute, and let's say the solute is NaCl, then of course you'd be using the concentration of NaCl and you're going to denote it like this. But since we're not giving the solutes, that's not our focus. We just would consistently use the general formula and just call it solute B. So yeah, so this is the first part of the question. Remember when I explained to you that the question has two major keywords. The first keyword is osmotic pressure, and then the second keyword is freezing point. And then remember, this question is actually asking you for the freezing point of the solution. It is not asking you for the concentration of the solute. But we need to determine the concentration of the solute in order for us to start working on the freezing point. So now, because we're dealing with freezing point, we have to use the freezing point equation. So the freezing point equation, okay, this is the second part of the calculation. The freezing point equation is simply changing T sub F is equal to K sub F multiplied by B. And this freezing point equation can also be known as freezing point depression equation. It can be known as that as well. So changing T sub F is simply going to be changing freezing point which is just simply Kelvin. So changing T sub F is the change in freezing point. For those of you who need to understand what's going on here, I want to quickly explain what it means to have change in freezing point. Remember that for any liquid, like in the case of the solvent water, it is going to have its freezing point. Like in the case of water, the freezing point for water by itself is 0 degrees Celsius, meaning that is basically it's 0 degrees Celsius. But then in a situation where that water is contaminated or is mixed with a solute, it is going to have a new freezing point or a new temperature. So the initial temperature will be 0 degrees Celsius, and then the temperature after would be a new one. So the change in T sub F is the change in freezing point, basically the change in temperature before when the solvent was pure and after a solute or an impurity has been added into the solvent. So this is what this change in freezing point is. It is just basically the difference in temperature of difference in temperature before and after mixing. So mixing in this case is basically the addition of a solute. So before and after mixing, or and after addition of solute. Okay, that is basically what this is. Before and after addition of solute. So that's what change in T sub F stands for. Next, we have K sub F, which is simply the freezing point constant of the solvent. So in this case, every single liquid or solvent is going to have its own unique freezing point constant. It's very important that you guys note this. Every single liquid will have its own freezing point constant. In this case, of course, our solvent is water. And if you look at the back of the textbook, the resource section, you're going to see that we have the freezing point constant for water. And then, of course, B is simply just the molality. Molality. So, molality of the solute. So yeah, that is just basically what's going on here. So we have broken down the information. You already explained what change in T sub F is. It's just the difference in temperature before and after the addition of a solute. We have the K sub F, which is the freezing point constant, and then B, the molality. But when you look at this question, you see that to solve for the change in T sub F, which is a change in freezing point, we would need to know the value for Kf, which we already know because it's a constant, and the Kf for water. Let me quickly explain that. The Kf for water, when I look at the resource section of the textbook, I see that it is 1.86 Kelvin kilogram per mole. So that is already good. We know what that is, but we do not know the value for molality. And this is where the issue starts. If you do not know the value for molality, how are you going to determine what change in T sub F is? But then again, we're chemists, we're scientists. We have to remember that when we're doing Gen Chem, depending on the teacher you got or the syllabus in your school, they might have taught you that molarity and molality are related. So we have molarity, okay, is equal to the density, okay, of the solvent, in this case water, multiplied by the molality. So basically, it's going to telling us that the molarity of the solute B, so the concentration of the solute, is going to be the density of the solvent that was used to dissolve the solute multiplied by the molality, which is basically what we're looking for. And the molality here is just simply B. So I say this to tell you guys that whenever you're not given the value for molality, but you know the value for molarity as well as the identity of the solvent, you can simply determine the molality or the molarity. You can go either way. If you're giving molarity and you want to determine molality, you can use the density. If you're giving molality and you want to determine molarity, you can also use the density using this formula here. So rewriting this, we have a concentration of B, okay, solute B is equal to the density of water, okay, multiplied by the molality of the particular solute. So of course, we're trying to determine what B is. So B is simply just going to be molarity, okay, of the solute divided by the density of water. So we can just simply substitute that in this equation here. So we can simply substitute that in our equation. Changing T sub F is equal to K sub F multiplied by B. So again, changing T sub F is equal to K sub F multiplied by B, aka changing T sub F is equal to K sub F multiplied by concentration of B divided by the density of water. So yeah, this is basically what's going on here. Of course, you're going to substitute. Changing T sub F is equal to 1.86, like I had explained to you guys before. The freezing point constant of water is 1.86, so I can simply substitute that here. So 1.86 Kelvin kilogram per mole multiplied by the molarity of B, which is just simply 0.048108, okay, 726 mole per liter. Again, that is the molarity, which we had calculated at the beginning here. The first phase divided by, all of this is going to be divided by the density of water. Now, I want to quickly mention something that might confuse some of you. Remember that we're dealing with a freezing point equation question, and the freezing point equation question is key in understanding that the density that we need to use is going to be the density of water, okay, at 0 degrees Celsius, because this is the freezing point of water. Freezing point of water again is 0 degrees Celsius. The reason why it's key for us to remember this is because density changes value with respect to temperature, meaning the temperature that when you determine the density of a particular solvent at a certain temperature, and then you also determine the density of that same solvent at a different temperature, expect to have two different values. So therefore, we're going to be using the density of water at 0 degrees Celsius and not the density of water at any other temperature. This is key because we're doing a freezing point question. So you have 0.99984 kilogram per liter, and this is simply the density of water at 0 degrees Celsius. Basically, what we're trying to calculate. So, of course, we're scientists, we're going to cancel out all the units. So we cancel out the kilogram here, cancel out the kilogram here, cancel out the liter, cancel out the liter, cancel out the mole here, cancel out the mole. So all we have left is just simply the Kelvin. So we end up just doing the calculation. So just let me rewrite this now. Change T sub F is just 1.86 Kelvin multiplied by 0.048108726 divided by 0.99984. When you do the mathematics on this and you input this information in your calculator, you have, don't forget this Kelvin, of course, is the unit. So you just multiply this and divide the answer by this at the bottom here. So changing T sub F ends up becoming 0.0894965 Kelvin. So this is basically the answer for the change in T sub F. So this is the value for the change in temperature before the addition of the solute as well as after the addition of the solute. Now you're going to be wondering, yay, we've answered the question, estimate the freezing point of the solution. No, what the question is actually asking us is to determine the freezing point value of the aqueous solution. So let me quickly explain something to you. Before this aqueous, we have this aqueous solution, right? This is what we're solving for. This is the aqueous solution. It has a temperature at which it freezes. But this aqueous solution was once water, pure water, which is just, yeah, this is just pure water, which is at 0 degrees Celsius. So it first was pure water and then it became aqueous solution because this change in T, remember, change in something is usually the initial as well as the final, and then the change of whatever the initial the final is just a difference in the value. So note that this situation here, the aqueous solution, is telling us after a solute has been added into pure water mixture. So the left hand side is the pure water, not mixture, sorry, pure water solvent, okay, while the right hand side is an aqueous solution mixture. So at the beginning we have the temperature of freezing point before, okay, any solute was added, we have that to be 0 degrees Celsius. And then when solute is added, expect for the temperature of the freezing point for this new aqueous solution mixture to be lower. And it's going to have a new value. So to determine it, you end up with the temperature, okay, after solute has been added to become an aqueous solution mixture is going to equal the initial temperature, okay, of the pure water before solute was added minus the change in T sub F. So this is basically the equation that we're supposed to work with. So the T after ends up becoming T sub F after, which is what they asked us to solve in this question, ends up becoming T sub F before. We already know. I've explained that is 0 degrees Celsius before, which is just the freezing point temperature of pure water. We know that free water freezes at 0 degrees Celsius, or the freezing point of water is 0 degrees Celsius. We know that to be 273.15 Kelvin when we convert from degrees Celsius to Kelvin, minus the change in T sub F, which is what we solved for. So minus 0.0894965 Kelvin. So when you input this in your calculator, you end up getting 273.0600504 Kelvin. And of course, since we're scientists, we have to put our work in the proper number of decimal places. This is 2 decimal places here, so we have to put our work in 2 decimal places here. So T sub F after, okay, is equal to 273.06 Kelvin. And this is actually the answer. As you can see, 273.06 Kelvin is less than the initial freezing point, which is the freezing point of pure water solvent, which is 273.15. That is the reason why freezing point equation is also known as freezing point depression equation, because a pure solvent or a pure liquid is going to have its freezing point. By the time you add a solute or mix something into it or add an impurity, even if it's simply dust, you are automatically going to lower the freezing point or the temperature at which this new solution freezes. If you have any questions, please put in the comment section. If you have any suggestions or concerns, also put in the comment section. I also want to quickly mention that there's going to be another question very similar to this on my channel. So do watch this one, watch that one, as well as watch other freezing point questions on my channel. So like I said, yeah, that's it. And if you're a student who's struggling in any of your STEM related courses, whether you're in middle school, high school, or university, I am the tutor for you. I help students succeed in all their STEM related courses and be the best version of themselves in academia. So if you would like to book my tutoring session as well as my mentoring session in order for you to succeed and excel, make sure you email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.